Is the conservation of momentum notes. This is going to be station number 1 for our next 2 days. You should have your notebook out and a pencil ready to take notes, and you should also have a textbook that is available. I'd like you to start by just doing some review. Please find page 138 in your textbook and just do numbers 15 and 16. You might want to reference the section those questions are from, and those are from page 130 and 131. I'd like you to pause the video here, and in a minute, and once you've written some answers down, go ahead and check your answers against what I have written. But again, you should pause, do your best to answer the questions, trying to engage that memory, and then check your answers against the answers. All right, so number 15 asks, in terms of momentum conservation, why does a cannon recoil when fired? Now, on the other slide, I said recoil means to move backwards. This would be if you're at a shooting range and you fire a gun, it will pop back at you a little bit. Now, it's much bigger with a cannon. There's usually a much larger explosion within the cannon. So the reason why the cannon has to move backward in order for the cannonball to move forward is because the momentum has to be conserved. And so at the beginning, before the shot, there is zero momentum. And so the cannonball moves forward. And so to cancel that momentum out, the cannon moves backward. Now it doesn't go flying away like the cannonball because its mass is gigantic compared to a cannonball, which, I mean, isn't a small thing, but compared to this massive cannon, it's pretty. Number 16 asks, what does it mean to say that momentum is conserved? This goes back to our word conserve and to, as we talked about with water or electricity, I think the best example was forests. The total amount of forests doesn't change, but we might have to plant some to make up for others that we've lost. So it can move from one thing to another, but the total momentum of the system isn't going to change. Again, unless a force from outside it acts. So I'd like you to, in your notes, title your notes Conservation of Momentum. And let's start by just remembering and write these notes down in your notebook. To change momentum should be the title. Again, this is a Roman numeral 1 here. And then you need letter A would be impulse. Let's go over. So remember, impulse is a force applied over time that changes an object's momentum. When we talk about changing momentum, we're very rarely going to talk about changing an object's mass. We're only going to be talking about changing the speed. And so all of the things that you will do or you have done over these 2 days have to do with changing the speed of the object, not changing its mass. So if we're talking about changing something's momentum, we're talking about changing, we're mostly talking about changing speed. And again, the force, in order to change the momentum, has to be from outside the system. If you can't keep up taking notes, this is the beauty of video, so you should pause and finish taking notes and then move on. So section 2 is the law of conservation of momentum. So here's the law of conservation of momentum. The definition is the total momentum of a system does not change unless an outside force acts on it. So that's the important law of conservation. Number 2, our example is that a cannon shoots a cannonball, and forces are from the inside of the system, right? So the total momentum, that tells us that the total momentum has to stay the same because that force is not external. If you take the cannon's mass times the cannon's velocity and you add the cannonball's mass times the cannonball's velocity, you're going to end up with a momentum of 0 because they're equal, but they're opposite. These forces, these velocities, excuse me, are opposite directions, so the total ends up being 0. Again, same thing. Go ahead and write this down. If you need extra time, you should just pause the video. So right now, I'd like you to turn to page 132 and 103. I'm going to read, and you can just follow along in this section. I'm on 8.5 collisions. So again, you should be on page 132. 8.5 collisions. The collision of objects clearly shows the conservation of momentum. Whenever objects collide in the absence of external forces, the net momentum of both objects before the collision equals the net momentum of both objects after the collision. This is what we were talking about with the cannonball and the cannon. Now, there are going to be two types of collisions, elastic and inelastic. And so for those of you who have done the lab that is on the computer, you've already seen this idea of elasticity. And elasticity is going to be whether or not they stick together or if the momentum fully moves from one object to another. So here we go. Elastic collisions. When a moving billiard ball, this is like a pool ball, collides head-on with a ball at rest, the first ball comes to rest and the second ball moves away with a velocity equal to the initial velocity of the first ball. So if you're looking at the page, if you're looking at figure 8.11, in letter A, so you have the red ball comes over, hits the white ball, the red ball is then stopped, and the white ball keeps going at the same velocity that the red ball used to be going in. This is elastic. We see that the momentum is transferred from the first ball to the second ball. When objects collide without being permanently deformed, meaning like changing shape, and without generating or making heat, the collision is said to be elastic, an elastic collision. Colliding objects bounce perfectly in perfect elastic collisions as shown in figure 8.11. Note that the sum or total of the momentum vectors is the same before and after collision. Remember we talked about adding vectors? This is another place where that comes into play. Then on the top of 133, inelastic collision. So this would be if you have done the online lab yet, there was a little place where you could adjust the elasticity. So when you first started doing it, it was 100% elastic, and then you were supposed to do one that was 0% elastic or 100% inelastic. A collision in which the colliding objects become distorted, meaning like change shape, and generate heat during the collision is an inelastic collision. Momentum conservation holds true even in inelastic collisions. Whenever colliding objects become tangled or coupled together, a totally inelastic collision occurs. The freight train cars in figure 8.12 provide an example. Suppose the freight cars are of equal mass m, and that one car moves at 4 meters per second toward the other car that is at rest. Can you predict the velocity of the coupled cars after impact? From the conservation of momentum, net momentum before collision equals the net momentum after the collision, or in the equation form, which is written below. I'm not going to try to read it. Since twice as much mass is moving after the collision, can you see that the velocity after must be 1/2 of 4 meters per second? Solving for velocity after the collision, we find that the velocity after the collision equals 2 meters per second in the same direction as the velocity before the collision. The initial momentum is shared by both cars without loss or gain. Momentum is conserved. Most collisions usually involve some external force. Billiard balls do not continue indefinitely or forever with the momentum imparted to them. The moving balls encounter friction with the table and the air. These external forces are usually negligible, which means you can ignore them, during the collision. So the net momentum does not change during collision. The net momentum of two colliding trucks is the same before and after the collision. As the combined wreck slides along the pavement, friction provides an impulse to decrease its momentum. Similarly, a pair of space vehicles docking in orbit have the same net momentum just before and just after contact. Since there is no air resistance in space, the combined momentum of the space vehicles after docking is then changed only by gravity. We're going to stop there. And I'd like you to take out your notes again. And I'd like you to write this down. You do not have to draw this picture. It's just here to help you. So underneath where you started your notes earlier, please write down momentum, conservation, and collisions. When objects collide, the net momentum of both objects before the collision equals the net momentum of both objects after the collision. Number two pole walls will hit each other, and in all of these pictures, the total momentum doesn't change. So when two objects have the same mass, we can calculate the final velocity easily. So if we're looking at this one, say the red ball was moving at 1 meter per second, the white ball wasn't moving, there's the collision, and then after, the red ball is not moving, so has a velocity of 0, and the white ball would be going at 1 meter per second, which is what the red ball had been going. Let's look at B. The two balls are going to hit each other in the middle. So before, red ball is moving at 4 meters per second, and white ball is moving at the same speed, but in the opposite direction, -4 meters per second. Sorry, there should be an equal sign there. And after the collision, they're both still going 4 meters per second, but now in the opposite directions that they used to be going. Now, sometimes maybe this red ball is going faster than the white one. So if you look at the beginning, before the collision, the red ball is going 4 meters per second, and the white ball is going 2 meters per second. And after the collision, the red ball is going 2 meters per second, and the white ball is going 4 meters per second. Notice that if you were to add up the velocities before and after, in each row, the total is always the same. When objects stick together, the new velocity will be the original velocity added up, so 4 plus 0, and divided by the number of objects. So 4 plus 0 divided by 1, 2 freight cars equals 2 meters per second. And this is only if the two objects have the same mass. It is beyond our scope of what we're learning to change the mass of the objects. So you can write this down. What I'd like you to do right now is to go ahead and email me the answer to this question. If you missed any of the notes, you should go back and finish those up. So go ahead and pause and email me this answer. And if you have additional time, then you can go back to the following questions I'll put up in just a second. So again, these are extra. If you have extra time, I'll put the answers in the front of the classroom. You can check how you're doing. I'd actually like you to start with number 57 and 63 down here. These are most directly tied to what we've been doing. And if you still have extra time, then you can work on these other problems. All right, I hope this was helpful and that you got all the notes down. Good luck. See you in class.